Welcome to Metric Fundamentals. So, in the United States, we use the imperial system, or the English system, of units. So these are things like feet, miles, pounds, cups, teaspoons, tablespoons, things like that. But unfortunately, conversions between different units can be a pain because the conversions are all different. For example, the number of feet in a mile is 5,280, and that's different than the number of inches in a foot, which is 12. And there are 3 teaspoons in a tablespoon, but there are 16 cups in a gallon. So all of these numbers are coming about for a reason, but they're not all the same. And in science, we often need to convert between various units, and so to make things much easier on ourselves, we use the metric system, or the SI system, in which all of the conversions are based on factors of 10. So, the fastest and most effective way to solve a chemistry problem is to focus on the units involved. And this is why we're going to talk a lot about the units and converting between various units, because the units themselves give us a key to solve most of the problems that we'll see in a first-year chemistry course. So, in the metric system, or SI, for the French, for the International System of Units, I can't speak French, so I'm not going to try reading this. We define the base units that measure the fundamental quantities. So there are 7 fundamental units that measure 7 fundamental physical quantities. All other physical quantities are based on those 7 physical quantities, and thus all other units are based on those 7 fundamental units. So we have derived units and fundamental units. The derived ones are all derived from those 7 fundamental units. And here are the 7 fundamental units. So we've got 7 physical quantities and 7 units. So when we measure mass, in SI we measure using the kilogram. Note that it's not the gram, which seems a little strange. And the abbreviation is listed here, kg. To measure length, we use the meter, and it's symbolized with a lowercase m. Note that the case here matters. This is a lowercase k. Down here, for Kelvin, we have an uppercase k. Time is measured using the second, with a lowercase s. Temperature is measured in kelvins, not degrees Kelvin, but kelvins, and that's symbolized with an uppercase k. Electric current is measured in amperes, which is symbolized with an uppercase A. Amount of substance, or how much stuff we have around, is measured in moles, and we abbreviated that MOL. It's not much of an abbreviation, but it's something. And then luminous intensity, so how much light there is being emitted by something, is measured in candelas, which is labeled CD. In chemistry, we generally don't use candelas too much. We use amperes only in electrochemistry, but the rest of them, the other 5, are used fairly often in chemistry, so you need to know those 5 and their abbreviations. So let's look at some of these in greater detail. So let's start out by looking at distance units, or length. So the metric base unit for distance, or length, is the meter. Again, symbolized with a lowercase m. And uppercase m means something else. 1 meter is about 39.3 inches long. It's a little longer than a yard. And a meter stick is numbered in centimeters, which we abbreviate cm. So the m there is meter, the c there means centi. So just like a dollar is divided into 100 cents, and a century is 100 years, a meter is divided into 100 centimeters. So that cent part means 100. So a centimeter is 1/100th of a meter, because we need 100 centimeters to make up 1 meter. We can then write this mathematically as 2 different equalities. We can write it either as 1 centimeter equals 1/100th of a meter, which is 10 to the minus 2 meters. Or we can write it as 1 meter is equal to 100 centimeters. Now note here that these equal signs have 3 lines to them instead of the normal 2, and that three-lined sign means that one side is defined to be equal to the other side, or that it's exactly equal to the other side. So 1 meter here is exactly 100 centimeters. It's not about 100 centimeters. It's not 100.1 or 100.00001 centimeters. It's exactly 100 centimeters to exactly 1 meter. So that's what we mean when we see these three-lined equal signs. Now each centimeter can be divided into 10 millimeters, symbolized with mm. So each millimeter is one tenth of a centimeter, or 1,000th of a meter. And then the equality we can write, the two equalities we can write, is 1 millimeter is defined to be equal to 1/1000th of a meter, which is 10 to the minus 3 meters. Or we could say that 1 meter is exactly equal to 1,000 millimeters. We could also divide our meter into 10 decimeters. So deci here means 1/10, where milli meant 1,000th. Note that it doesn't mean 1/1,000,000th. And we label, or we abbreviate, the decimeter as dm, both lowercase, d and m. So 1 decimeter is defined to be 1/10 of a meter, which is 10 to the minus 1 meters. Or we could say that 1 meter is defined to be equal to 10 decimeters. We can also then relate our decimeters to centimeters. If we have 10 decimeters in a meter and 100 centimeters in a meter, then it must be that we have 10 centimeters in 1 decimeter. So 1 decimeter is exactly equal to 10 centimeters. Or 1 centimeter is exactly equal to 1/10 of a decimeter, or 10 to the minus 1 decimeters. So if we need to measure a large distance, so significantly larger than a meter, then we can use the kilometer, symbolized km, both lowercase again. 1 kilometer is 1,000 meters, so our equality is 1 kilometer is equal to 1,000 meters, which is 10 to the 3 meters. Or we could write it as 1 meter is equal to 1/1000th of a kilometer, which is equal to 10 to the minus 3 kilometers. So we can write our equalities either with 1 kilometer is equal to some number of meters, or as 1 meter is equal to some number of whatever prefixed unit we have. You need to be able to memorize, and you actually need to go ahead and memorize, the meter stick equalities. So 1 meter is equal to 10 decimeters, which is equal to 100 centimeters, which is equal to 1,000 millimeters, and 1,000 meters is equal to 1 kilometer. You need to know these, you need to have them memorized, because you're going to need these throughout the rest of your chemistry career. You also need to memorize the 1 prefix definitions. So 1 decimeter is equal to 10 to the minus 1 meters, or 1/10 of a meter, or 0.1 meters. 1 centimeter is equal to 10 to the minus 2 meters, or 1/100th of a meter, or 0.01 meters. 1 millimeter is 10 to the minus 3 meters, or 1/1000th of a meter, or 0.001 meters. 1 kilometer is 10 to the positive 3 meters, or 1,000 meters. So I like using these definitions for our prefixes and not these definitions. These just get a little bit harder for me to use, but these are relatively easy for me to use. So these are the ones that I use because these are all in scientific notation already. So it's fairly easy to convert from one unit to another once you understand the rules for how to convert using scientific notation. To help in remembering the meter stick equalities, you may want to visualize a meter stick. So picture a meter stick. So you've got your meter stick. It's divided into 100 centimeters, into 10 decimeters, and 1,000 millimeters. So remember what the numbers on a meter stick mean. So not sure if you can read this, but we've got larger numbers with, at the 10, 20, 30, 40, and so on, there are numbers ranging from 1 up to 100, and then we've got smaller lines in between those that are not numbered. So, to help you remembering the definition of a kilometer, then visualize 1,000 meter sticks, so 1,000 times this length, lined up end to end. So that's going to be quite long. So a kilometer is very big. A meter is roughly 3 feet long. It's a little bit more, about 10% longer than that. A centimeter, or rather a decimeter, is a few inches, 3 or 4 inches long. A centimeter is smaller than an inch. It's a little less than half an inch. A millimeter is much less than that. It's more like a 1/16 of an inch. You can replace the word meter in any of the above equalities with any other base unit. So we can say something like 1 liter is equal to 1,000 milliliters, just as 1 meter is equal to 1,000 millimeters. We can say 1 centigram is equal to 10 to the minus 2 grams. We could say 1 kilocalorie is equal to 10 to the 3 calories. So now let's look at volume units. So volume is the amount of space in 3 dimensions that an object occupies, which means that volume is a derived quantity. It's not a fundamental quantity because its definition depends upon the distance. It depends upon length. So we have a length in 1 dimension, we have a length in a 2nd dimension, and then we have a length in a 3rd dimension. And so volume is derived from length, its length cubed. So any unit of volume can be converted into the cube of a unit of distance. So a cube that is 1 centimeter on each side, so 1 centimeter by 1 centimeter by 1 centimeter, has a volume of 1 cubic centimeter, which we label this way, centimeters cubed. So note here that while cubic centimeter is often abbreviated as cc in biology and medicine, centimeters cubed is used in chemistry. We don't use cc in chemistry. Instead we use cm with a superscript 3 to label it. A cube that is 1 decimeter on each side, so 10 centimeters by 10 centimeters by 10 centimeters, has a volume of 1 cubic decimeter, so 1 decimeter cubed, and 1 cubic decimeter is equivalent to 1 liter. This is how we've defined the liter. So 1 liter is defined to be equal to 1 cubic decimeter. And note here that the abbreviation for a liter is an uppercase L, not a lowercase l. And then just like for getting from a meter to a millimeter, we can do the same thing with liter to milliliter. So there are 1,000 milliliters in 1 liter, and we abbreviate milliliters with a lowercase m and an uppercase L. So the unit has whatever symbol it has, an uppercase L in this case. For meter, it's a lowercase m. And then we add on to the left side of it whatever the symbol is for the prefix. So in this case, the symbol for milli is a lowercase m. So we have lowercase m, uppercase L for milliliter. There are also 1,000 cubic centimeters in 1 cubic decimeter. Because 1 decimeter is equal to 10 centimeters, 1 cubic decimeter is equal to 10 to the 3, or 10 cubed, cubic centimeters, which is 1,000 cubic centimeters. And that's because we have 10 centimeters times 10 centimeters times 10 centimeters. So we have 3 tens multiplied together. That gives us 10 cubed, or 1,000. So 1 cubic centimeter is equivalent to 1 millimeter, because we need 1,000 cubic centimeters to make up our 1 cubic decimeter cube. Our 1 cubic decimeter cube is 1 liter. If we divide that into 1,000, because we have 1,000 cubic centimeters, that will be the same volume as our milliliter. So 1 milliliter is equal to 1 cubic centimeter. And you should be able to convert from one to the other. All you really have to do in this case is change the unit from cubic centimeter to milliliter. So you need to memorize the following volume relationships: that 1 millimeter is equal to 1 cubic centimeter. You need to memorize that 1 liter is equal to 1 cubic decimeter, which is equal to 1,000 milliliters or 1,000 cubic centimeters. So now let's turn to mass. Mass measures how much matter is in an object. It's not measuring how many atoms are around. It's a measure of how much matter is there. But it's not the weight, because mass and weight are not exactly the same thing. They're related, certainly. But weight is a measure of how hard the force of gravity is pulling on an object. Which means that if the object is moved from one place in the universe to a different place, either a different place on Earth, or to another planet, or to the moon, that means the weight may change if the force of gravity changes. If the acceleration due to gravity on an object changes, that means the weight of that object will change. So weight and mass are not the same. Mass does not change in different places, because the object contains the same amount of matter even if you move it. So the mass of the object can't change when you change the location. Provided, of course, that you're not chipping bits off or adding bits to it. This is not a piece of clay that we're separating. This is a basketball. If we move a basketball from the surface of the Earth to the surface of the moon, we haven't changed the mass of the basketball. We've changed the weight of the basketball because the moon has a lower acceleration due to gravity on its surface. It's about 1/6 of the acceleration due to gravity on the moon's surface compared to on the Earth's surface. So that basketball will weigh about 1/6 of what it weighs on Earth, but the mass will be exactly the same. Because again, it has exactly the same amount of matter in it. So we measure mass using the gram. Again, note that the SI unit is the kilogram, but in chemistry we generally use the gram because we generally have smaller quantities, at least in most laboratory settings. We're using less than a kilogram's worth of material, so we generally measure in terms of grams. So 1 gram is approximately equal to the mass of 1 milliliter of water at room temperature. But this is only an approximation. It's not exact. Depends on the density of water, which depends on the temperature. So in this class, it will usually be acceptable to approximate 1 milliliter of liquid water. It's got to be liquid water as 1 gram of liquid water. So 1 cubic centimeter of water is equal to 1 milliliter of water, and we're going to say that that's approximately the same as 1 gram of water. Note that the scripty L here in parentheses means that the water must be in the liquid state for this to be true. And we have similar abbreviations for solid, so an S in parentheses, and for the gas phase, so a G in parentheses. So now let's look at temperature. In the United States, we generally measure temperature using the Fahrenheit scale, where the melting point of water is 32 degrees Fahrenheit. Note that the melting point and the freezing point is exactly the same. The boiling point of water is 212 degrees Fahrenheit. Note that these two are 180 degrees apart, just like if you have an angle that is really just a straight line, that's 180 degrees. So we have 180 degrees from freezing to boiling. Room temperature is somewhere between 68 and 77 degrees Fahrenheit, depending on how warm the room is. The human body temperature is generally 98.6 degrees Fahrenheit, although there's some fluctuation. Different people run hotter and cooler. But in science, we don't use the Fahrenheit scale. We measure temperatures using the Celsius scale or sometimes the Kelvin scale. In this class, we're generally going to use the Celsius scale, although in future classes we may transition more to the Kelvin scale. So in the Celsius scale, the melting point of water is defined to be 0 degrees C. The boiling point of water is 100 degrees C. The room temperature is somewhere between 20 and 25 degrees C. And the human body temperature is about 37 degrees C. So now let's look at time. The base unit for time is the second, and we abbreviate it with a lowercase s. Sometimes you'll see second abbreviated with SEC. Technically, this isn't really correct. We really want to write it with just that lowercase s, because we don't need anything else. Lowercase s means seconds. when we're talking about a unit. It doesn't mean anything else, so we don't need that EC. So now let's talk about unit and prefix abbreviations. You need to memorize the following abbreviations for metric units and for their prefixes. And note here that metric abbreviations do not have periods at the end, as do other abbreviations like Mr., Mrs., Doctor, Street. Those things all have periods at the end of them for their abbreviations, but the metric abbreviations do not. We don't put the period in for abbreviations in the metric system. So M is meter, it's not M period. So M is meter, G is gram, S is second. Capital L is liter, which we know is a cubic decimeter. We know that lowercase m, uppercase L is a milliliter, which is equal to a cubic centimeter. You should know these prefixes, that lowercase k is kilo, lowercase d is deci, lowercase c is centi, lowercase m is milli. So one strategy that might help you in problem solving is to start each assignment, quiz, or test by writing any recently memorized rules at the top of your paper. You don't have to bother writing all of your memorized rules, but you should write the recently memorized ones at the top just to ensure that you don't forget them when you're under a little bit more pressure as you get into the test. So the first thing you should do is, when you get your test or quiz, is sit down, write out the recently memorized rules. Any rules that are memorized before the last week or two, you ought to have fully in your long-term memory, and you shouldn't have to write those out. Those should already be cemented in your brain. So any rules you memorized a while ago, again, should have been committed to memory, and you shouldn't have trouble remembering these later when you need them. If you do have trouble with them, then you need to go back and review them. You need to get them firmly rooted in your long-term memory. So in this class, we're going to use equalities to solve many problems. The rules for writing equalities have been presented above. We've already talked about them. And let's get a little bit of a note here on memorization. We try to minimize what you need to memorize, but it's not possible to completely eliminate memorization from chemistry courses. There are some things which you just don't have time to look up all the time. You need to know what that lowercase m, capital L stands for. You need to know that ml stands for milliliters. You need to know how to work with a milliliter, convert it to a cubic centimeter, or convert it to liters. You need to know how to do these things. You won't have time to look them up all the time. It will take you far longer to do things if you have not memorized certain things. So again, I'm trying to minimize how much you have to memorize. I care far more about whether you can apply your knowledge than whether you can spit things back. But there are certain things that you just need to have memorized so that you can apply the knowledge. Otherwise, you'll just get bogged down in all the details. So when you memorize, it helps to use as many of your senses as possible. Say the rules out loud, as you might rehearse for a play. Write the equations down several times, in the same way, in the same order, every time. Organize your rules. Organize them into patterns, rhymes, mnemonics, whatever helps you best. Number the rules, so you know which rule you might have forgotten and when you need to stop. Because if you know you have 6 rules and you've got all 6 written down, then you can stop. You don't have to keep asking yourself, do I have all of them? It also would help you to picture real objects. So sketch out a meter stick. Write the first 2 metric rules and compare them to your sketch. Make sure that the equalities that you've written down match up with your sketch of a meter stick. For volume, you could mentally picture a 1 centimeter by 1 centimeter by 1 centimeter cube, so a 1 cubic centimeter cube, and you could call it 1 milliliter. You can fill the cube with water to have a mass of 1.0 gram. Ultimately, you want to be able to recall these rules just like that. You want to not have to write them down on your paper, and you just know what they are, and you can go ahead and use them. So that was metric fundamentals.